So now we're messing with compound interest. Before we did simple interest, which is oh, so we're at compound interest now. With simple interest, you earn interest each year on your original investment. But with annual compound interest, which is what we're doing today, you earned interest both on your original investment and on any previously earned interest. Example. Assume we deposit $1,000 at 5% annual interest. This is how the account would grow with both simple interest and compound interest. So let's look at simple interest, which is on this side first. There we have that our initial investment was $1,000. Our rate was 0.05, so that's going to give you $50. So you have $1,000 and you add $50. Okay? Since you add $50, now you have 1,050, which is what we have right there. Then the second year or the second time this is processed again, you process again at 1,000. So times 0.05, you have 50. But now it's 1050 plus 50 equals 1,100, and so on. Compound interest is a little bit different. Compound interest is, you start with 1,000. That's your initial investment, so it's still the same. 1,000 times 0.05, we know that's 50, and you add that. So we have a 1050. However, the difference comes into the next time. The next time we process this, we don't start at 1,000. We start at 1050, which was what we have previously, not initially. So 1050 times 0.05 is 5250. So now we're going to go 1050 plus 5250, which is 11 with $2.50. After that, we have 11 with $2.50 times 0.05. That's 5513. So now we have 1157 with 63. You can see that compound interest grows faster. And since we only did this 3 times, it didn't show that much. But imagine after time, this will give you more money. So here it says, we can see that simple interest is computed each year on the original investment, but compound interest is computed on the entire balance at the end of the preceding year, meaning the simple interest always produces $50, which is what we see from here and here. But compound interest increasingly amounts in later years, which is what we're seeing right there. We started with 50, then became 5250, then 5513. So let's try to do this one. It says example 1. If $7,000. Okay, so we have present value. This is interest. So remember that interest, the formula is interest equals present value, rate times time. Correct? So we have present value on this one is 7,000. Is deposited in a savings account that pays rate 0.04 because it says that it has 4% interest compounded annually. How much money is the account after 9 years? But this is compounded, not simple interest. And the formula was simple interest. This is simple interest. Okay? So, how are we going to do this? Well, first of all, let's calculate for this. So this is going to be time will be 1. So I have 7,000 times 0.04 times 1. So therefore, my interest for that is 7,000 times 0.04 times 1 is 280. Okay? So therefore, for this year, now I'm going to get this. And remember that future value equals future value plus present value. So this becomes that I have 7,000 plus 280 equals 7,280. Okay. Now we're going to do this process again. Okay. But now my present value is not 7,000. My process is going to be 7,280. My rate is going to be still the same. And time's going to be 1. Okay. So let's mix everything together. So I'm going to put 7,280. Sorry, this was wrong. This is present value plus interest. Okay, so I have, again, the formula is future value equals present value plus interest. So I'm going to put plus, and then I'm going to put, to find the interest is going to be 7,280 times 0.04 plus 1. Times 1, sorry, not plus 1, times 1, my bad. Okay. So I can factor this, and I have 7,280 times 1 plus 0.04. Which, if you recall, this is just the formula for the other formula for future value, which was, okay, so we're just, this is nothing new. This is something we've already seen. Okay. And once we calculate this, we have that future value equals $71.20. Now, let's do another one, okay? So this is going to be my present value again. Equals now 7571.2. My rate again is 0.04, and my time is equal to 1. So we still have future value equals present value, 1 plus RT. Let's fill this thing in. So now I have 7571.20, 1 plus 0.04. Okay. So we have 7571.2 times 1 plus 0.04. Now, let's make this small, so we can see more. And let's see if we can find a pattern, because I don't want to do this 9 times. So let's see if we can find out a pattern in this. Okay. So here we have, let's get this another color so we can, we have, these are our results. Oh, this one, and this one, right? So let's write down what we have. So let's write this. Let's say we've present value, because that's on all of them. But present value is right there. Present value is right there. and present value is right there. So present values and all of that. Plus, now do you notice that how fast this thing is growing? What is another constant that's there? Well, that constant is the rate. Each time the rate is growing by 0.04. So 0.04. And then what we have after that is the present value again. So this is going like this. Okay? That means I can factor this out and we get this. Do we agree with that? And if I add those two, I have so this is this. So this, by this I mean this guy right here, is how the account is growing. Okay? So let's do a little chart, if you may, so we can see. So for year 0, which is the investment, initial investment, we started with 7,000. Then from year 0 to year 1, we grew by 7,000 times 1.04. And we already have that, so let's calculate it. 7,000 times 1.04, 7280, which is what we had before. So we're going in the right direction, and it's working for now. So this is 7280. Then from year 1 to year 2, we went from 77,000, which was my original investment, times 1.04 times 1.04. So 7,000 times 1.04 times 1.04. So on this one we got 7571.2. Let's see if we got that. Look at that. It's right there. So we're going in the right direction. So let's do year 3, which we already have. Then year 3 we have 7,000 times 1.04 times 1.04 times 1.04. So that's 7,000 times 1.04 to the third power, because we have that 3 times. So that's going to give me 7874.05, which is what we had right there. So guess what we're going to be doing to get the 9 years? So to obtain year 9, we're going to do 7,000, 1.04 to the power of 9, because 9 years. So I have 7,000 times 1.04 to the power of 9. So here we have 9,963 with 18 cents. So this is how much this person will make in 9 years. Now, this is a little bit too complicated, too hard to memorize how many powers and all that. So there's a formula for this. This is known as the compound formula. The compound formula states that if PV dollars are presented at interest rate I per period, then the compound amount future value after n compounded period is this. But I don't like it like that. So let's rewrite this formula again. So this is how we're going to be using this formula. Future value equals present value times 1 plus rate over m to the mt. This is going to be using, so we know what future value is. Future value, has not changed. PV, we know it's present value, again, something that has not changed. R is rate. T is time in years. Again, none of those has changed. The only thing new is M, where M is how many times the account is processed. So we go back to our example on this one. Per year. So we go back to our example before. We had that this was processed once per year. So my M on this one would be equals to 1. But it's to the power of 9 because how many years did it do? 9. So it was not 1 times 9 is 9, which is what we have here. So again, this is how we're going to be using the formula, okay? Now, let's compare both formulas right there. They have it as an R, I have it in an I, but remember, it's pretty much the same. Why do you think compound interest grows faster? Well, that's actually simple to see. The reason it grows faster is because of this is an exponential function. Okay? So, let's do an example. A lot of theory and jargoning. So let's do this. I have, suppose $1,000 is deposited for 6 years in a savings account paying 8.31 per year compounded annually. So this is what we're going to put as an M. So I have future value, I have present value, I have rates, and I have time, and I have compounded. So my future value, I don't have that. That's what I'm supposed to find. Present value is 1,000. My rate was at 0.0831. And this is going to be time is, here it is, 6 years. And this is going to be compounded annually, so that's a 1. So filling in everything into the formula, which was, the formula is future value equals present value 1 plus R over M to the MT. I'm going to fill everything in. So I have future value equals 1,000. 1 plus 0.0831 over 1. And then 1 times 6. So I have 1,000, 1.083 to the power of 6. You put that into the calculator. 123 times 1.083 to the power of 6. And we have that our future value for this thing is 1,613 with 51 cents. Okay. Now, we need to find the interest. Remember that the interest is equal to future value minus present value. So my future value now it's 1613.51 minus my present value which was originally 1,000. Then my interest on this is 613 with 51 cents. So let's do. So we have future value, present value, rate, and time at M. And we have that our future value on account grows, so that's the future value of 50,000. Present value, they started with 16,000. Time is 18 years. And they want us to find the interest rate. So this is 1. So we're looking for this. Okay? So this will become, again, the formula for compound interest is future value equals present value 1 plus R over M to the MT. So we have that 50,000 equals 16,000. 1 plus R over 1, 18 times 1. So I'm going to divide both sides by 16,000. The zeros go away with those. So I have that 50 divided by 16 is 3.125 is equal to 1 plus R to the 18th power. Now, we have two options to solve this one, but one's going to make it overcomplicated and the other one's going to make it easy. We could use logs to take down that 18 down, but that's going to leave a log inside the variable inside a log, which will complicate things. So this time, since this is exponential, I'm going to be using what is known as roots or exponents in fractions. So, rule, if I have this I can rewrite it as so. Okay? So that means that I'm going to put this 3.125 to the power of 1/18. So I have 3.125 to the power 1 over 18 equals. And the other rule of exponents that we have to remember is that if I have x to the m to the power of n, this becomes x m times n. So I have 1 plus r. 18 times 1 is 18 over 18. So now I have 3.125 to the power 1/18. And then 18 divided by 18 is 1, so that means no more powers. So 1 plus r minus 1 to both sides. So I have that r is equal to 3.125 to the 1/18 minus 1. So let's put all of that into the calculator, and I have open parentheses 3.125 to the power of 1 over 18 minus 1. Therefore, my rate is equal to 0.065535, which we have to, since it's a rate, we have to put it into percent. So rate is equal to 6.535%. And that's the whole thing. So interest can be compounded more than once a year. Semi-annually, which means 2 periods, which means on this one, m is equal to 2. Quarterly, which means that m is equal to 4. Monthly, that means m is equal to 12. Daily, which is m is equal to 365, and so on. Okay? And within that, we can still have, let's say, for 9 months. We still have to consider 12 and so on and so forth. And I already demonstrated, I already introduced the real formula. So let's continue. Remember that if we want to find interest, this is just future value minus present value. This is the same thing. Why? Because future value represents all of this, which is all of this. Okay? So I have, in July 2016, Bankrate.com advertised a money market account at Ally Bank at an interest rate of 0.85. Find the value of the account in 10,000. In 10,000 is if 10,000 is invested for 1 year and interest is compounded according to the periods below. Okay. So on this one, we need to find future value because we need to find compounded accordingly. So we're going to define future value. So let's see what we have. Future value, that's what we're looking for. We have present value, which was $10,000. Our rate was at 0.0085, and time was for 1 year, I believe, right? Yes, it's right there. So I have the formula, which is future value equals present value, 1 plus R over M, MT. So I have future value equals 10,000, 1 plus 0.0085. This is annually. So on this one, m is equal to 1. So this is 10,000. 1.0085 to the power of 1. So 10,000 times 1.0085. So my future value for this is 10,000 with 85 cents. I mean, $10,085. Semi-annual, that means that this one has an M of equals 2. Same thing. I'm still looking for future value. Present value is still 10,000. Rate is 0.0085 and time still 1. So I have future value equals 10,000. 1 plus 0.0085 divided by 2. 2 times 1. So let's do the math. So let's start with everything inside the parentheses. So 0.0085 divided by 2 plus 1 to the power of 2 times 10,000. So I have that my future value for this is 10,000, 85. Well, that's too many zeros. $10,085 with 18 cents. So it is growing, not that much, but it is growing. So now I have Monthly, that means that M is equal to 12. So I have future value, which I'm still looking for that. Present value, which is 10,000. I have the rate, which is still 0.0085. And I still have time, which is 1. So I have future value equals 10,000. 1 plus 0.0085 over 12. 12 times 1. So again, let's get that in. We start inside the parentheses, and we know that division comes before addition. So 0.0085 divided by 12 plus 1 to the power of 12 times 10,000. So that means that my future value equals 10,000.33. Finally, daily, that means that my M is equal to 365 because that's daily. So I have future value, which that's what I'm still looking for. We have present value, which is still 10,000. My rate is still 0.0085. Time is equal to 1. So I have future value equals 10,000. 1 plus 0.0085 over 365. 365 times 1. So finally, 0.0085 divided by 365 plus 1 to the power of 365 times 10,000. Then I have that the future value equals 0.36. Imagine if we had to do that the old-fashioned way, one at a time. I would talk. Okay? Now, there is another formula for that includes compound interest, and that is continuous interest. Continuous interest states that if we have future value equals present value equals e to the RT. By continuous, it means that this is done one after the other. As fast as a computer can calculate this is how it's going to be going one, and another. Okay? So this has no end. Okay? So we're going to follow this formula. The formula states that it is future value equals present value e to the RT, where everything's the same with exception of the e, and this is just a mathematical constant like pi. Okay, so let's calculate this. Actually, it's in the calculator. It is right in the ln. Okay, so it's just a constant, nothing new. So let's see what we have. We have future value, present value, rate, and time on this one. And it says, suppose that $5,000 is invested. Okay, so that's my present value because that's what's going to be invested in a savings account at an annual interest rate of 3.1%. So it's 0.031. Compounded continuously for 4 years. Find the compound amount. So find the future value. Okay, so we have future value equals 5,000. E 0.031 times 4. We put that into the calculator. 5,000 times e to the power of 0.031 times 4. So that means for this one, my future value will be 5,660 with 8 cents. And this